Okay, so this is the last section of chapter 2, which is adiabatic changes. So the notation that we use is when Q is 0, so no heat is supplied or subtracted to the surrounding, and that's what we call adiabatic changes. And I think this is a nice kind of the situation where we can recap what we talk about isothermal versus adiabatic process. We already talked about isothermal reversible work. What is the amount of the work for the reversible isothermal expansion? And that was, we covered that before, and I'm going to go and recap on that concept. But now the contrasting example is, this is an adiabatic process. And I want to start with something that you've been knowing for all the time. PV core NRT, when T is constant, everything is constant here. So therefore, one important equation is PV equal constant. Right? So that one I know for the isothermal, if you want to be more clear, reversible expansion, then I mean this is we're talking about isothermal situation where system maintain the same temperature, so I don't need to actually define it. But still, that's really a key. To just I'm going to derive it. The key is temperature change is not zero, and it is a key for you to figure out what is really the temperature change here. Okay? How much of the temperature does it happen? And we are talking about, mainly we are talking about expansion, just to make our process much easier to understand. When the expansion process, when things that expand, okay, on the system I'm doing the expansion, so my internal energy should go down. So therefore, not only that, your temperature is negative. Okay? Well, in other way, your final temperature is smaller than your initial temperature. And that's another fine print. But the final governing equation that you want to remember is, it's pretty similar. P times V is constant for constant isothermal process. When it's an adiabatic process, we put in the use word of gamma, and they are constant. Okay, so this is a final equation that I want you to sort of keep that in mind. And what is a gamma here? Gamma is heat capacity ratio. Okay? And I told you before, typically monoatomic ideal gas, that's a 3/2R, and this is a plus 1 more R, so that's a 5/2R. So a typical example is, let's say, 5/3. So in always your gamma is bigger than 1. Okay? So your gamma is bigger than 1 for adiabatic process. So what I can draw now is, this is my choice for y-axis is the pressure and x-axis is the volume. I'm going to draw the graph. And your initial volume is small. This is your initial volume. You are going to expand it to the final volume, and your pressure should come down. Okay? So that is what we call it expansion. So this is an initial. This is your final. This is your volume. I like this because I guess that represents area under the curve is a work. Work on the expansion. I guess area, to be clear, area corresponds to the magnitude of the work, right? Because this expansion is a negative number, and we don't want to be tricked by this. Okay, but now, I'm going to draw the two curves here now. Same initial volume, same final volume. And one process is isothermal expansion, the other is an adiabatic expansion. one is experiencing much more steeper decrease in the volume. The other one is sort of the milder volume change. And which one is going to be? Think about it. This one is, let's say this is essentially a certain constant divided by volume. This one is P. And your gamma is bigger than 1. So it is, and this is, for example, like 1.5 or 1.25, depending on the heat capacity ratio. But what I'm saying here, this is your reference point, okay? This is your reference point where this is an isothermal. I think that you probably draw this in your general chemistry. So now this adiabatic expansion, your pressure drop is much more significant, okay? And that is your adiabatic process. And I want you to also think about, because this constant is essentially nRT, so if you change the temperature, I can draw a bunch of isotherms. Can you see I draw the dotted line here? This is another isothermal expansion line at different temperatures. So some lower temperature, and this is a higher temperature. Right? And you can see that this is why they're changing from initial temperature to final temperature. They are different, and we need to figure that out from here. So that's the one. And so once again, adiabatic process, Q is 0, but really the part that you need to figure out is what is my delta T? Delta T is here's delta T 0, and it has a pros and cons. So this is a table that I made it, and I love this one. So let's draw the table here. So I'm going to say isothermal. I'm going to say adiabatic. Okay? And then we are going to talk about initial to final expansion, for example, volume change. We are talking about volume change here. Right? So volume change for this process. And then it is this is essentially you have to deal with 4 quantities. And one quantity that is obvious is we need to calculate delta U. We need to calculate Q. We need to calculate work. And let's say this is all reversible process. Okay? So this table shows up concerning about all reversible. And this is what we learned. And these 3 things are all related this way, right? I'm trying to give you a hint that you don't have to calculate this one independently, right? Once you calculate, there are easier quantity to calculate, and there is a freebie essentially. You can take it, knowing that this one is true. And I also wanted to think about there is one important thing that you need to know and calculate. Do you know what it is? What completes this kind of understanding this process of gas expansion under isothermal or adiabatic? And that one is, you should really need to focus your attention to delta what? T. Right? If you know the temperature change, you are in business. Okay? You are in business too. So that's something that I need to know. So let's talk. What about the isothermal case? What is my delta T? 0. Yeah. And I need to say ideal gas, I guess. Otherwise, if I say the van der Waals gas pressure calculation work is not so easy because it involves a lot of calculation. So it's an ideal gas. So what is my delta U change? Why?
Because you didn't change temperature. And
That's right.
Energy is based on the thermal.
Not only that, if I say the ideal gas, can I say delta U is simply CV times delta T? Right? So that's one. So, whatever it is, because this is 0. So then you just need to calculate those two, right? I guess the reversible work. This one, do you remember we calculate this one is minus nRT natural log VF VE. Right? And then you have a freebie here, right? Negative work, which is positive. Yeah, well, I'll be lazy, I'll just put it this way, right? But in my note, actually in my note, I put it right there. nRT. So one thing to really recap here is because if this is an expansion, we are talking about negative work, and the heat is positive, right? So if things are isothermal expansion, heat has to be supplied onto the surrounding to compensate what's supposed to happen in the internal energy, but you maintain to be constant because you're supplying extra heat. This is actually in the engine, you supply the fuel. When things are expanding it, they generate heat, right? And that's the portion that you give into the system while you can do the expansion. Temperature essentially, temperature is all over the places where we can say, oh, that's an isothermal expansion combined with the adiabatic expansion. That's what the Carnot cycle in chapter 3 is about. Okay, so let's go back here. There's one easy one that I have an answer right now already. What is that?
Q.
That's right? Here we go. Oh, I don't need to calculate anything. This is your friend, all right? And then once you know this Q is 0, either you calculate that they are the same quantities, up and down, right? So I need to figure out which one is easier to calculate. That's my logic. And then what about delta T? I know delta T is not 0, okay? And this is something that I need to calculate. You need to calculate delta T for adiabatic expansion. But this one is the first thing that you need to calculate. And if I ever calculate my delta T for this volume changing process, I can easily say what's my delta U, which is CV delta T. Right? So this is your first step to calculate, and I'm going to show you that how to calculate the pressure drop or the temperature drop in an adiabatic expansion. And once you know the final temperature, delta T can be changed, which is the delta T is your final temperature minus your initial temperature. So you need to calculate that from here. But once you got the delta T, that's really the key, right? This is really the key. Look at the key. This is really the key. Doesn't look like key at all. Okay. But this is really important. Okay. This is all the key. Right. This is a key. And once you know your T, this one can be calculated. I know this is 0. What about my work? Volume change, right? You remember the volume change, delta V or dV is your work, right? You don't need any one of them. All the volume is given because there's a backdoor, right? There you go. Right? So everything adiabatic change coming down to one consideration, which is how do I know my final temperature? Right? And let's get that on to this one. So the next one is we are going to talk about how we can calculate my final temperature. Okay?